Hello everyone, I'm Xiaoqi from Princeton University. Today I'll talk about measuring RTT in the data plane. There are many reasons why a network operator wants to measure the round-trip time of network flows. Here, let me mention a non-exhaustive list of examples. First, RTT can be used for security reasons. An abnormal, unexpected increase in RTT could signal a BGP hijack attack downstream, when traffic are rerouted to another autonomous region, or AS, either accidentally or maliciously. Also, IP spoofing attack could be detected when RTT to the attacker differ from that to the victim. Furthermore, round-trip latency also closely reflects the network's performance. A daily pattern of increased RTT signals network link congestion in peak hours. Meanwhile, we can also use RTT alongside other performance metrics to infer the user's quality of experience, or QoE, when using network applications. For example, we might infer the quality of streaming video the user is playing. In this work, we focus on passive RTT measurement by observing traffic at an intermediate vantage point, possibly at the boundary of an enterprise or edge network. We assume a client sends packet to a server on the internet and receive replies, and we observe both packets at the vantage point. This is likely true if we are close enough to the client or server, and less likely in the middle of the network due to asymmetric routing on the internet. Passive monitoring allows us to measure genuine RTT experienced by the application packet themselves, without additional traffic overhead caused by active probes. We split RTT into two halves, the external leg and the internal leg. We measure them separately. This is similar to a pirate work called Ruru. At the vantage point, we run our algorithm in a programmable switch data plane directly using P4. This allows us to measure each and every packet at line rate, producing multiple RTT samples per flow. This is useful for long-running TCP flow, such as video streaming or file download. If you only get the first RTT sample from the SYNAC packet, like the pirate work, you won't understand what happened later in the flow. Also, measuring directly in the data plane allows us to enable real-time actions on the packets. For example, we can potentially reroute a packet based on the RTT measured in the P4 data plane. Our work uses TCP sequence number and acknowledgement numbers to measure RTT. Traditionally, pirate work only measures TCP RTT using handshake packets. So when seeing the SYM packet at the vantage point and the acknowledgement packet from the internet, we can try to deduct the external leg of RTT. Afterward, when the client finishes the three-way handshake, we can have a sample for the internal leg RTT. Here, the x-axis illustrates time. After the handshake, we can get more RTT samples if we match an outgoing data packet with its acknowledgement. So say a packet goes to the internet with a certain sequence number, and the server will reply with a corresponding acknowledgement number. With these samples, we can get another sample for external RTT. Likewise, for the other way around, when sequence numbers comes in and the client acknowledgement back to the server, we'll see another sample for internal RTT. Now, let's focus on measuring the external RTT first. The algorithm for measuring the other way around, measuring internal leg, is symmetric. To produce RTT samples, we maintain a table of all pending outgoing packets, waiting for their X. Each row here is indexed by the TCP flow ID 5-tuple, as well as the expected ACK number. We also store a timestamp in the table. Say for now the time was 1:05. When the packet is going out, we can see its flow ID, sequence number, and we see the payload length as well. We can calculate the expected ACK number, or EACK, by adding the sequence number with the payload length. Now, we'll try to insert this record into the table. We just write down the flow ID, the EACK number, and the current timestamp. Later on, when at t equals 125, when the packet just come in, we'll see a flow ID and acknowledgement number. Now we can try to look it up in the table. We have to flip the flow ID around because we have a flow ID writing the other way around. We can see there's a match. So we can subtract the timestamp in the table from the current time to see the RTT is 3. We'll also try to erase this entry so we can save the memory for future insertions. Well, that sounds simple. However, we have a huge challenge here. It's about the delay act. TCP have a mechanism called delay act that acknowledgement was not sent back immediately. It could be delayed for as much as 50 milliseconds. Well, the first challenge here is the measurement becoming inaccurate because of the delay. Our solution is to only look at long packets. When those packets are likely MTU size, their acknowledgements are likely not delayed. That's because these packets are very likely being sent back to back. So when there are two consecutive packets arriving, there will be one act. That act is not delayed. There's more severe issue though. Many packets never receive their corresponding act. In fact, close to 50% of packets never receive any acknowledgement, since the server only sends one act for every 2 packets. So there will be a lot of entry in the table that's not deleted. Our solution here is to use lazy expiration for entries. The first step is, when the entries are not deleted, we'll just look at the timestamp. When the timestamp becomes too old, we consider entry expired or timed out. That's because if the timestamp was much smaller than the current time, for example, if 1 second or older, that means we're never getting an act for this particular entry. However, no one will delete this entry either. We cannot use the controller or some outside help to delete entry in the data plane, because that would be too slow. Instead, we just leave those entries there. When we try to insert other entries, we may have hash collision with this entry. When there's a hash collision, we'll try to check the timestamp of the current entry. If the current entry's timestamp was too old, we consider the current entry expired and simply override this entry. We just mentioned hash collision. So in practice, using a single hash table to store packet records will lead to a lot of unnecessary hash collisions and reduce the probability for an outgoing packet to successfully insert the record. Therefore, we'll get less matches. We use multi-stage hash table here to reduce the hash collisions. Let's illustrate an example with 4 stages. So say right now we have a lot of entries, some of them already expired. When a packet shows up, we'll try to look at the current time, flow ID, and also calculate the expected act number. Then we'll use different random hash functions to calculate different positions, 1 per stage. Say we got these 4 positions. We'll try to insert this packet record into the 4 positions. For the first stage, we cannot insert because it's already occupied. Similarly for the second and third stage as well. For the fourth stage, we see it's an empty place, we can insert it. Well, it's not actually empty, it's just the current record have a very small timestamp, so we consider it as empty. We'll insert the current packet's record there. Multiple stages allow us to have multiple chances to insert the same packet, so this actually reduces the chance for hash collisions. Even if we have the same memory space, we can allocate it to 3 or 4 different stages and achieve a much higher insertion success probability. After a while, say the corresponding incoming ACK packet come back. So this packet is acknowledging the last packet we just see. We'll first look at the timestamp and then the flow ID of this packet and try to calculate the locations using the same hash function. So we find out the same positions. Now we'll try to look up the entries in these positions. We'll check every stage until we find a match. On the first, second, and third stage, the entries are either expired or it's not a match. On the last stage, we find out it's a match. So we'll just subtract the timestamp and get the match RTT. We also don't forget to erase the entry there. So that completes our process for getting one RTT sample. Now let's present some evaluation about our algorithm. We captured some traffic trace from Princeton University's campus internet border. It's a 10 gigabit per second bidirectional link. The metric we want to measure is the percentage of RTT samples successfully matched, compared with an offline analysis script that look at the entire trace to find out all the possible RTT matches. So basically, we want to see how much hash collision causes us to lose samples. There are 2 parameters for our multi-stage hash table. The first parameter was the size of the table, which means how many entries are there in the table. The second the second parameter was the total number of tables. Here, in the x-axis, we plot the size of tables with larger and larger entries possible. On the rightmost side, we have 65,000 entries. That's the maximum possible table we can get on our hardware device. On the y-axis was the successful match rate, or how many RTT samples we successfully produce. The higher the better. If you only use one table, this is the success rate. It's actually quite low. We can get as much as only 25% matches. With more and more table, we can actually get higher and higher match rate, and we can get as much as 99% match rate when using 8 tables. We have deployed our algorithm in Princeton University's campus network. To minimize risk for the production network, we mirror the traffic from a 10 gigabit per second campus border link and feed the mirror traffic into a Tofino P4 switch. We measure both legs of the RTT separately. When measuring the external leg, we can analyze different cloud service latency distribution and histogram. When measuring the internal leg, we can diagnose Wi-Fi clients' latency anomalies, which might be caused by a wireless access point or the access point controller. In summary, today we present an algorithm that matches the TCP sequence acknowledgement numbers to produce many RTT samples per TCP flow. The algorithm runs in the switch data plane and uses multi-stage hash tables to reduce the effect of hash collisions. It uses lazy exploration to solve the issues that most entries are never deleted by an incoming ACK. We tested and deployed our algorithm on 10 gigabit per second campus border links using mirror traffic and a barefoot Tofino programmable switch. Our P4 code for the Tofino switch is open source. Please check it out. I'll be happy to take any questions.